The occurrence of nuclear fission and fusion can be explained in terms of the binding energy per nucleon, which is the binding energy of a nucleus divided by the number of nucleons in it. Click the graph button to see the variation of binding energy per nucleon with mass number. Nuclei with high binding energy per nucleon are very difficult to break up. Isotopes of the iron group have the highest binding energy per nucleon and hence are the most tightly bound nuclei. Iron 56 has binding energy per nucleon of 8.6 MeV, which is exceeded only by iron 58 and nickel 62. This explains why there is an abundance of the iron group elements in the universe. Click the iron group button to show the position of the iron group elements in the graph. Nuclides near the iron group with mass number A between 40 and 80 are stable as they have relatively high binding energy per nucleon. This means that a great amount of energy is needed to break up these nuclides. Click the Stable Nuclides button. Nuclides to the left and right of the iron group have lower binding energy per nucleon and are less tightly bound. Thus, less energy per nucleon is required to break them apart. The left part of the curve suggests that a pair of light nuclides can be combined to form a single heavier nuclide that lies nearer the iron group to achieve higher stability. Such a process called fusion occurs naturally in stars. Energy is released during such process. Click the fusion button to reveal the part of the curve where fusion occurs. The right part of the curve suggests that if a heavy nuclide were to be split into two nuclides that lie near the iron group, the resulting nuclides would be more tightly bound. Such a process is called fission and it involves the release of tremendous amount of energy. Click the fission button to reveal the part of the curve where fission occurs. Summary: Nuclides around the iron group with mass number between 40 and 80 are stable as they have relatively high binding energy per nucleon. Light nuclides have low binding energy per nucleon and can be combined to form a single heavier nuclide to achieve higher stability. A heavy nuclide also has lower binding energy per nucleon and can split into two nuclides that lie near the iron group for higher stability.